Hi and good morning and welcome to this Howarth webinar titled UCV Operating Theatres, Design, Validation, Verification and Sustainability, which is being held in association with Health Estate Journal, the monthly iHeed magazine, of which I'm the editor. Howarth Technology, which was certainly one of the pioneers in UCV technology, says the aim of today's webinar is to address what it dubs the knowledge gaps among clinical staff, engineers and contractors in both public and private health organisations to help them fully understand the specific and detailed requirements of air ventilation systems. In his presentation, the company's service and after sales manager, technical manager, Mike Dunn, will focus on the history of UCV systems, why do we ventilate a critical space, understanding the objectives of design and validation, sustainability in the future of the NHS, and why you should annually verify. He says his view is that knowledge sharing will eventually result in a higher calibre of product for the NHS and healthcare sector, with less downtime, happier environments, and a more sustainable future. During the webinar, please type in any questions you may have as it proceeds of the speaker using the questions tab on the right of the screen, and at the close of Mike's presentation, I'll put as many of them as I can to Mike to answer. If there are any he can't come back on immediately, he will be in touch with you. I'm sure you'll find this a very interesting and informative session. Mike, over to you.
Thanks, Jonathan. So I'm just going to get my controls straight. Okay. So good morning, everyone. Thanks again, Jonathan, for that introduction. My name is Mike. I'm the Service and After Sales Technical Manager at Howarth. And like Jonathan said, we're going to be covering UCV operating theatres, design, validation, verification, and sustainability. So a little bit of a background from me before we go into the main part of the presentation. I'm electrically biased, which is unique for someone in my position. So I was an electrical apprentice in 2006, working in HV and LV switchgear and control systems, and then moved across into becoming an electrical commissioning engineer for the same business. Again, looking at control systems, changeover systems, so completely different to operating theatres. I then joined Howarth in 2009 in their production team, working with the guys putting the exhaust together and the control systems are attached to that. In 2010, I became a commissioning engineer on both the pharmaceutical and the medical side of the business. And then in 2011, I became a solely medical commissioning engineer. So since that date, I've been involved with new projects, predominantly new projects going into hospitals all over the world, really. In 2016, I became the medical commissioning team leader, so there was an importance on compliance and managing the team and checking that VMS interfacing was correct and that type of thing. So that was my duties in that position. And then in 2018, I became the Service and After Sales Technical Manager, which is where I still am today. So the outcomes of the session today that we're going to cover. We've got a lot to squeeze in the sort of next 40 minutes. So we're going to cover initially the history of UCV systems and the relationship between Hugh Howarth and John Charnley, two pioneers in this area. So we're going to quickly touch on that relationship and Wrightington Hospital. We're then going to look at why we ventilate these critical spaces and why we go to all this effort to make sure that things are right and spend a lot of time designing, validating, commissioning, verifying. So we're going to look at that. Then we're going to try and understand the concept of design and validation, which is HTML3 Part A. That's the document for design and validation. We're going to assess the main and key points of that document. Then we're going to move on to something that I'm really passionate about, sustainability and the future of the NHS. I've just literally last week finished my dissertation in this subject, so I've done lots of research and studying around that the last 2 years. So I'll be interested to see what people think about that, and I'll show you what my findings were. And then finally, we're going to touch on HTML3 Part B, which is obviously the main duty of the service and after sales team at Howarth. I'm going to try and understand why we carry out these verifications in these critical sites that we look after and deal with. So a history of UCV then, all based around early 1960s, but obviously we're still very heavily in use today. So it's important to note that there's multiple manufacturers of UCV systems in the UK. There's not just Howarth. However, regardless of any of the manufacturers that you decide to go with, the UCV systems must comply to Chapter 12 of HTML301 Part A in the 2021 version. For those of you that don't know, HTML3 was re-released in 2021, just coming up to sort of 2 years ago, and previous versions of HTML3 are superseded by that document. When we were going out and doing validations, there was sometimes a derogation in place to cover the new elements of the new document, and there was discussions around the 2007 version, but we're going to speak about that a little bit later on. I think it's probably time now we look at 2021 and use that as the key document when we look at them. So UCV systems then, and where it all started. This is Wrightington Hospital, a hospital in Wigan, a centre of excellence for orthopaedic procedures, still to this day a centre of excellence for that type of work. And it was the meeting of two men, these men, in 1961. The chap on the left of the screen there is Sir John Charnley, who's from Bury in Lancashire. And obviously we have Dr. Hugh Howarth that sits on the right-hand side of the screen there from the Howarth family. Howarth are based in Bolton and have been since 1858, but moving through time, the area that we're focusing at is 1961. Howard's founding business before 1961 was to ventilate and purify the air in cotton mills and the brewery industry, or the brewery manufacturing type industry. The Howard family had created something called an Archimedean screw ventilator that sat on the pitch of a roof, and it moved in a clockwise fashion, and it ventilated the space for all the people that worked in there, and sort of around the industrial times where they were starting to look at the indoor air quality issues that were apparent. So Howard capitalised on that. And then we moved through time. He was the son of James, who started the business. And John Charnley had an issue with post-operative infection rates, and he was seeing a high spike of people sadly passing away or struggling with infection after the operations, and he changed everything. John was a pioneer in this area. He was manufacturing his own replacement joints. He was chiseling the tools to do the procedures himself, and he eventually related it down to the air that was in the operating theatre that was going to be the problem. So these two guys got together in 1961 at Wrightington, and basically John says to Hugh that there's an issue in the operating theatre. I believe it's the air, and it's going to be too difficult to solve through anything that you can come up with. So Hugh disagreed, and he said, no, I believe that we can put this together. I work in cotton mills and breweries. This is just a scaling exercise. I need to take what I do in a brewery, and I just need to scale it down to an operating theatre. John still wasn't having it, said, no, it won't work. And Hugh said, well, I'll tell you what, I'll make it, and then I'll donate it to Wrightington, and if it doesn't work, nothing's been lost. So between the two of them, they come up with this, and this is what we affectionately know as the greenhouse, and it's a very interesting piece of kit from my point of view. I'm going to take you through the components of it now. You can see, if we look at it, it's a freestanding unit in the middle of an operating theatre, and over here on this tiled wall you can see a duct that goes to the outside atmosphere. That is the external ducts, or the supply at the positive pressure. If we try and think, while I'm talking you through this, about an operating theatre now and the way that an operating theatre works: high level supply, low level mechanical outpaths, and then natural relief through the operating theatre. The filtration above the patient at number 2 is a cotton sock. Still, as today, the anaesthetist sat outside the footprint of the operating theatre with the anaesthetic machine, the anaesthetist, and the patient's head. Inside the tent was Charnley and a scrub nurse. There is a pass-through hatch here at about hip height, so if you needed anything, a runner could pass that through. And then again, like a normal operating theatre, we have a negative pressure outpath at the bottom. This system, once it was installed, post-operative infection wound sepsis went from 9.7% to 3.5%. And Howarth went on further, that I've not covered in these slides because we're very pressed for time today, but we went further on and created what we called a BEC system, a body exhaust system. Once the greenhouse and the BEC system were introduced, that post-operative infection rate went down to 0.5%. So obviously there was a relationship between the air and infection rates, but it wasn't feasible to keep working inside that greenhouse. So I believe this was a very uncomfortable, warm, not a very nice atmosphere to be working in. So the greenhouse evolved in the 70s and moved to this. So this is called the DF10. The 10 relates to 10 feet by 10 feet, and you can see that it's starting to look a little bit like an operating theatre now. It still had cotton sock filtration, and it still stood freestanding in the operating theatre. The patient still went in the same manner, and then we would have plates of plastic, almost boards, that would clip onto the front of the X-flow of the unit here. Sorry, not the X-flow, of the unit here. We'd call those discipline panels, and the air would move in the same fashion using the negative outpath here for the air to move away, so it would bathe the surgical site. Moving through time, we then have the X425S, the 90, the 90-5, and the 28. The UCV in the picture here is an X428, and these panels on the outside of the canopy here, we would call infill panels. Infill panels were manufactured out of Perspex, and they stop 2 meters above the finished floor level, and you can see the differential color in the vinyl on the floor there. That's obviously a requirement of HDM, but that indicates the clean zone. So if there's a clinical team laying their instruments up on right on the edge there, we know that the HEPA filtered air is coming over the instruments. Then in 2012, I was part of the team that developed this as a test engineer, and this is the X428 Evolution, and it utilizes Coanda technology to move the air and create the same level of protection as a screened unit. So air jets out of the Coanda system at a high velocity, and it creates this sort of movement of air in this direction. Notice this particular operating theatre has a low level outpath over here, which is a mechanical extract going back to the general HVAC equipment, not back into the UCV. Our equipment recirculates at a high level up here. And I just dropped this slide in because a lot of people don't understand the way an air moves across a surgical site and in relation to the way an X-flow functions. The air moves in an exponential manner, so that picture on the left there is an exponential decay curve, a simple sort of mathematical movement. And a lot of people will think that these are laminar, and they'll call them laminar flow or noisy box in the ceiling, or we didn't know that that was there, or there's loads of different things I've heard these called. But air moves in an exponential manner on an X-flow. That's why it's called X-flow. The first 2 letters are the starting name of the equipment. So air moves at its quickest point over the surgical site or the patient, and then it decays as it moves to the outside. Negative pressure from the centrifugal fans draws back in up here. And when the air is recirculating through the canopy, about 66% is going back through, 33% comes from the HVAC system. Now I'm going to talk about why we ventilate critical spaces, but before I do that, I just wanted to quickly touch on this picture here. This was a barn theatre that Haworth delivered in 2022, and it's unique in the fact that some people may never have seen a barn theatre before, so you can get a 2-theatre barn or a 4-theatre barn, and you have to take special design consideration when you're putting a barn theatre in. We worked with a mechanical designer, an M&E designer on this one to make sure the barn was equally laid out and there was going to be nothing that would interact with the UCVs in certain positions in certain scenarios. So if you look at HTML3 Appendix 10, it gives you a cause and effect. When you do a barn theatre, you need to look at the cause and effect of what happens if this barn down here, if the fans trip or the PD panel trips and it goes off, does this patient still remain protected from the outside environment whilst they're still open having orthopedic surgeries being undertaken on them? Everything that you can see in that picture was supplied by Haworth through our package and our capitals team, and we still service that to this day. That's at Airedale Hospital in Yorkshire. So reasons to ventilate then. There's multiple reasons why we do this, obviously, and I'm going to walk through these 6 boxes. So the first one being control of non-viable contamination, and that could be dust or fumes, solid or liquid. When we talk about dust or fume, that sometimes could be related to an LEV system, but we know that ventilation systems are a mitigation tool for controlling the way that aerosols are distributed around an environment. So that's the first reason. The second reason is to control viable contamination, and viable contamination are things like live microorganisms, bacteria, viruses and spores, Legionella, E. coli, that type of stuff. Now, it's there to mitigate and control against these, but it can also amplify the issue. So if we have holding water in an air handling unit, and the air handling unit is blowing over the entrance of a hospital and that's got Legionella in it, then obviously it can cause an issue as well. So it's important that we keep on top of our maintenance schedules. The third reason is for clean airflow paths. I'm going to touch on this a little bit in the next couple of slides. Open door protection for clean spaces. So when we talk about layup prep rooms, that's the cleanest part of the operating theatre, in more cases than not. And then the dirty utility is the dirty space. So if the dirty space was adjacent to a clean corridor, we would keep that under -5 pressure. So when the door opens, we wouldn't get any backwards coming into that room. So everything that's nasty in the dirty utility, we're keeping it in that space. And then equally with the prep room, if we're opening packs up, we want to make sure that the pressure cascades out from the clean to the less clean areas. The fourth reason is for COSH, substances such as anaesthetic gases, and you've got to consider as well exhaled anaesthetic gases in recovery spaces. As the patient breathes out the anaesthetic gas that they may have been breathing in for a couple of hours, it's important that the mechanical ventilation system takes that away and it isn't projected straight into the breathing zone of a recovery nurse. And the way that we do that is the next box, cross-flow ventilation. We take a high-level supply and a low-level extract in anaesthetic rooms and recovery spaces. Gas is denser than air and it will drop and be drawn away by the mechanical ventilation system. It's important that the two systems work together and they don't interact with one another and cause issues within the space. And then the last reason is to stabilise the environment. Stable temperature and humidity is a building services design tool anyway, and then we need to control the moisture and combat SPS, which is sick building syndrome. So moving on to HTML3 Part A then, 2021. This is the design and validation document. The new document is here, sitting on the left, and it supersedes its predecessor there on the right. You may hear other versions of this document spoke about as HTM 2025 and going all the way back to 1984, which is way before my time, DV4. And I must admit, I don't know a massive amount about DV4, but 2025 I know a little bit about. HTML3 Part A was completely rewritten in 2021. So some of the key parts of that rewrite. The main document now covers new installations and consists of 13 chapters and 10 appendices, which is a massive increase in the 2007 version. Like I said, completely rewritten. 2021 document gives a much more in-detail approach to design and gives you clinical reasons why ventilation is required. So if you look at table 2 in that document, it will say we need an endoscopy at 10 air changes and it needs to be negative for this reason, and we need it at that noise level and it needs to control within this temperature range. So the guidance is much clearer now. Chapter 4 introduces my favourite part, the ventilation safety group, which I'm going to explain to you why in a moment. And then if you're an AP for vent on site, chapter 12, and you've got new equipment being handed over, read and understand that chapter, because you have a validator on site, they're the boxes that they should be ticking, and they're the bits that you should also understand. So the key areas again going through, so we've got refurbishments and changes of use. So where previously some people may have taken a broom cupboard and turned it into a treatment room, we can't do that now, and this guidance is much clearer in tables like table 2. The ventilation safety group should manage every single aspect of the critical ventilation system, and that should tie in with the ventilation strategy, which is obviously tied again directly to net zero and reducing consumption and making our hospitals more efficient. There's an expanded operating theatre section, and then there's installation standards, such as making sure that I can get to the VCD handle within the space. You'd be surprised how many hospitals were manufactured with a VCD against the wall, behind a light, that once it was all in, you couldn't get to. And also we have ductwork pressure testing, in situ air handling unit testing, and lots of other different things, permeability testing of the room, all that should be done. And then finally, acceptance and validation. A big part of the new HTM is in section 13.32, where critical air handling units now have an expected life of 20 years. This has always been in CIBSE Guide M, but never taken note of really. But now it's in HTM, we have to act on it. Part B defines that every 10 years we should be fully breaking up that air handling unit and giving it a full recommission. That might be nitrogen cleaning coils, stripping it out, replacing the fans and motors, 3 ports off, running them through the full sequence from the BMS, a full deep clean of the AHU at 10 years old. So if we have a hospital that has 60, 70 air handling units in and it opens today, we need to capture when that's going to happen. So it might be in the 17th year we need to start replacing. Appendix 2 notes that newly installed endoscopies must be negative. There's a new air change rate from 25 to 22 air changes in operating theatres, and the noise level in UCV theatres matches that as well, 55 to 53. There's 4 new air handling units that we can take advantage of, which I'm going to cover shortly. 8 new operating theatre layouts that goes from 2025 all the way to current day, and barn theatres are noted for the first time also. Lots of other things we need to consider. Identification, labelling and inventory. That label on the air handling unit has a minimum height of 100 millimeters now, which may seem excessive, but it's a question that needs to be answered. Resilience and diversity, N+1, think about it from an electronics point of view. If we have something that goes down, we don't want the space to shut, so we need an N+1 diversity in there. Guidance on the change of areas, life cycle of AHUs and mid-plant life assessment, airflow rates tailored to new fan and control technology. We're not allowed to use belt and pulley fans now, got to be plug fans, EC fans. There's a more detailed information on the commissioning process, and standalone air conditioning units are abolished, as are fan core units from clinical areas. External AHUs must be specifically assessed. So there's AHUs out there on rooftops without heat tracing on, glass traps. There is louvers that are incorrectly positioned, drawing water through the intake. This is out there. I've seen it with my own eyes. We need to stop this happening. And then finally, ductwork must be pressure tested. Medium pressure ductwork, class B, 3%, and that's noted in DW143, so that's a visa document. Now, the ventilation safety group, like I say, my best bit, my favourite bit. And the reason is because these people should be making sure that everything that comes from contractor to NHS to private healthcare, whoever it is designed as for purpose, fit for purpose, in line with their scope, and that no one's trying to wriggle out of anything contractually along the route. So they need to look at if the design process is adhered to, design modifications to existing premises are undertaken correctly, the installation, commissioning and validation process is carried out and completed, operational maintenance and management, annual verification and performance testing is carried out at the right time each year. And I think LEV should fall part of that as well, so we have a different period in LEVs. More often than not, it's 14 months in line with HSG 258, but that should be captured as well. Prioritising the plant replacement programme, decommission and removal of redundant equipment, and then the assessment of any contractual derogations at the start of the process. So at the start of the project, agree where the derogations sit. You can't get to the end of a programme or the end of a project till you get to commission and validation. Something's not working, you need to start derogating it at that point. It needs to happen at the start. And the reason this is my favourite bit is because as a subcontractor, we were constantly asked if the space could be used or it was fit for purpose, which we can't make that decision. It needs to be a decision by the VSG. We're engineers, we're not clinically led on or IPC or microbiologists. So the way that this would work is, as a subcontractor, I would sit out of the circle here, I could tie in at various points, but this would be my main point of contact more often than not, the AP for vent. He would be supported by the AE for vent, who would be an independent, not attributed in any commercial way to anyone in the chain, and he would probably be employed by the estates management team, but he would support and sign off this AP. So, for example, if I come in and I say, there's 3 positions on the UCV in Theatre 4 that's failed, straight to the AP, he'll say immediately, can we use it? And I'll say, I don't know, you need to speak to the ventilation safety group. When he does that, he will probably speak to the AE, maybe his manager, he'd let the theatre manager know, and then at some point we'd have to make a clinical assessment whether we were going to continue to use it, and that would be by these people. Now, if it's completely knackered, we need a new canopy in there, and it's going to cost tens of thousands of pounds, the estates management then can go to finance and ask for some funding, and that, I believe, is the best way that that can be set up. It's in section 4.5 of HTM, if anyone wants to go and read that after this webinar. Now, the various elements of air handling units we're going to talk about is in that section of the book, Appendix 1. And there's some new solutions for us in this new document. So I'm going to take you through the components of this one and then we'll look at the others. Excuse me. So we have motorised dampers that sit at each end of the air handling unit. And the frost coil has been changed to a fog. We have a primary filter, then the supply fan, we have the runaround coil, the cooling coil sits on the discharge side of the fan to keep it under positive pressure, so any water that comes off that won't pool, it will go through the drainage system, reheat battery, final filter, damper. This method of heat recovery is the least efficient, you can see 63%, as it'd be an extract system across the other side of the plant room. And that would give the heat recovery back to this. next air handling unit that we have is a thermal wheel. And notice that all the components are at the bottom of the air handling unit. That's done on purpose to make maintenance easier and inspection easier too. 65 to 75% efficient. And in COVID, CIBSE told all institutes to turn these off. However, when you speak to some authorised engineers within the industry, they believe that by the time it's gone through this system and diluted, that argument is irrelevant. So HTML3 was written before COVID, but that's just something to consider. Again, I'm no expert when it comes to the transmission of COVID. The next two air handling units we've got is a new one. This is a cabinet air handling unit manufactured by multiple manufacturers now, but the main company who started this off was DAX. And you can fit two of these in the footprint of a heat plate exchange. Notice that it's got the least efficient method of heat recovery, but if you're doing a refurbishment, it's a really useful thing that you can look at. A couple of years at the IHEAM conference, they had one of these on the floor, and I had a good look through it with one of our guys from the office, and to be fair, it looked like a really good solution. The next one along the line here is a heat plate exchanger, my favourite because I'm a bit of a net zero geek, and it's 80% efficient. Notice again that everything's on the positive side of the fan, supply side of the fan, sorry, that needs maintenance. So we've got this drip tray, eliminator cooling coil that would be drained away, and the final filtration. The grades on these filters here would normally be G4, F7, but there's an authorised engineer out there that fits F7, F7 to give an equivalent of F9. Now onto the theatre layouts, and I just want to speak to you again about these clean spaces. So this is general operating theatre, and you can see that we have the anaesthetic room and the prep room over here. The main operating theatre is attached to the prep room here in a layout fashion. So you can, if you notice these numbers in the square boxes here, this is the room pressure, nominal room pressure. This is operating at 35 pascals and this is at 25 pascals. So by default, this pressure stabilizer here would be 10 pascals between the space. The dead corner in the operating theatre has a mechanical low level out path, and then we have a natural relief here onto the service corridor. Now, one thing that's important to know is this is the perimeter of the operating theatre around that square there. You can see that the scrub is open, and the reason we're not including the scrub in the perimeter of the operating theatre is because there's a natural means of ventilation going out onto the clean corridor, so patient transport corridor out here. If that wasn't there and we had a mechanical means of ventilation, then again we wouldn't include it. The reason that that's important to know is because when we take this supply volume as a design volume, we multiply it by 3,600 to give us meters cubed per hour, and then we divide it into the room volume to get the right air change rate from a verification and a design point of view too. So if we increase the size of this room to get to 22, we need to put more air in. So that's the perimeter of the room. That's important to know. Notice that the anaesthetic room that's at the top here has a balanced supply and extract. And remember what I said before, cross-flow ventilation, high-level supply, low-level extract. Ideally angled as well. HTML3 gives us an idea that it should be angled, so that's important to note too. So before I move to the next slide, conventional theatre, layup prep. We now put a canopy in the room and it sort of makes things slightly different. Again, this is standard layout from the HTM. We measure the room volume in exactly the same fashion, so there's no concerns there. But notice that this clean space over here has now turned to a sterile pack store, an SPS. The volume in the room has dropped considerably, so that's gone from 280 litres to 100 litres. And where we previously had a PRV, or a pressure stabiliser in the wall, we now have a transfer grill. And notice that the pressure is now 25 in both rooms. So what that means is we have an equalised pressure across this door. Now the reason it looks like that is because the Royal College of Orthopaedic Surgeons say that sterile pack stores should store the equipment should be taken through and opened under the footprint of the UCV. When we have a layup prep room, there's enough air change rates in there and there's enough door protection in that room, and the air change rate will be really high, so you can open the pack, check everything's in there, and then be ready for the next procedure to come through. Because this is HEPA filtered, Royal College of Orthopaedic Surgeons say that should happen in here, and that's in HTM2. Now, it's not uncommon for a hospital to have a door here into the prep room, a door there, and say, actually, we want this to be a layup prep room. So once this is in position and the patient is under the bed, they want to make almost like a conveyor belt through the room. So we'll open packs, move the patient in, and move through in that fashion. That's an important thing to know, because when the overpressure comes in, that should be baffled, because that can impact the way that the UCV functions and works. An important thing to consider when you've got a UCV is to take the supply duct as far away from the other rooms as possible, the ancillary rooms. So the canopy sits here in the center. This is an example. Induct velocity should be no greater than 2.5 meters a second, and the primary air should be balanced to this system in a fashion that's easy to do. So you've got VCDs within the duct, and you can see that the ancillary rooms are in other areas of the floor. This was a project that Howth did a couple of years ago. So to summarise then the part A in sustainability, consumption versus air change rate, we need to look at the patient against the air change rate. Education and opinion, we need to look at cause and effect and how we tie these things in. Fabric losses and ageing infrastructure. Mechanical plant is falling apart, with some of the plant we see really needs to be looked at and worked out. And then the ventilation safety group is another key part of that document. So the existing estate then, and what I found, this was formed part of my dissertation. This is a 60-year-old hospital, and you can see the amount of fabric heat losses that they're experiencing. So when I've gone through, I had about 70 pictures of this site. This was causing massive issues within this sort of area in this hospital. So that's obviously a big issue. The good thing about this hospital was they'd started cladding and they'd started replacing windows, and I could physically see through the thermal imaging that things were getting better. So there is hope at the end of the struggle. And then the picture on the right hand side was a hospital that I worked with down in the southwest of the country. The same operating theatre with the same canopies and the same procedures. Basically, one week it had the BMS tied to it, and the next week it didn't. And when it had the BMS tied to it, you can see that the incremental gains that we got, and this is one of the conclusions I've got in my dissertation. The difference in energy saving between these two is 60%. So you can see that 98% of theatres are set up like this: set back, full speed, set back, full speed, and it'll run like that for its entire life. Where at this hospital, they were taught to go to set back. This dip here is the lighting going off, to set back, and then to completely off, and then back up, and to completely off. So they saved about 60% of the energy. That's where we're going to make the gains in the NHS, I believe. The future of the NHS looks pretty rosy, and this is a hospital designed by an intelligent bunch of engineers from WSP. I've actually had them on my CPD day, and we got to discussing this, which was quite interesting for me. But you can see every single inch of the roof is maximised by solar PV. We have air and ground sourced heat pumps controlling the heating and cooling. We have bee, bird, and bat hotels, sustainable methods of transport to the hospital, natural ventilation moving through the facade, rainwater captured. That's going to be great. That is great. But when we get to our scope on target for 2040, it's these hospitals we need to fix, not necessarily those, which is brilliant. Everything we're doing with that is great, but it's the older estate that we need to look after once we found the money. So HTML301 Part A then, 2021, sustainability conclusion. We need to look at UCV systems and the specific assessment. Remember that ductwork and where it sits. AHUs require specific attention and planning if it's going outside, heat tracing, etc. The ventilation safety group has to be multidisciplinary. It can't just be one, the authorising engineer running the show. It's got to be multiple people. Duct runs and mechanical systems are needed for special considerations. BMS and control systems need to be intelligent, and the VSG needs designing, but it can't just be left to the designer. It's a full group effort to get these things to work correctly. Now onto HTML301 Part B, operational management. So the document again on the left is the new document, 2021, replaced by its predecessor in 2007. Now it's rare that you'll hear ever a crossover of these. This was a line and sound straight over to this. Sometimes you can apply the original design factor, but you're allowed to do that anyway through this document. There's some significant changes to note in this, such as the new appendices. Noise levels have been changed from 75% real world to 80%. Chapter 3 gives some good information about minimum standards. And every time I do a validation now, I include HTML3 Part B, Chapter 3, Appendix 1 and Appendix 2, because if those criteria are met at validation, they will continue to be met in the future. So we're ticking all the boxes right at the start. Excuse me. Now, I'm not going to go into every single element of each chapter with you because you can see them there on the slide. There's 5 chapters within the document. Chapter 1 is an introduction. We have Chapter 2 is functional responsibilities. Chapter 3 is the minimum standards. Chapter 4 is annual inspection and verification requirements. Chapter 5 is the routine maintenance and inspection. Now, from an AP event point of view, and these really important people that are the eyes and ears and everything on site, it's important that those people also recognise other tie-ins to this document, such as HTM00. HTM00 states things such as you should invite educated or competent people to site to work on these systems. You should have records of their qualifications if required. You can't just be left to your own devices under HTML3. You need to sort of have a look at the holistic approach. And I think more often than not, most APs are multidisciplinary anyway, so probably more than aware of that. But there may be some people on the call that aren't. Again, in HTML3 Part B, these are the appendices. So we have Appendix 1 that covers air handling units, Appendix 2, which is fabric, and then Appendix 3, which is an equipment release certificate, which you don't really see that much, to be honest, but I think is still quite a useful certificate if you want to try and start using that or implementing something very similar to it. So, verification and an annual assessment. Why do we carry this out? I could have put loads of text on these slides, but I thought it'd be better with pictures. So you can see the AHU intake on this air handling unit here is disgusting. It's obviously full of lint or some sort of, I don't even know what it is. It's obviously not up to scratch for a critical ventilation system. The middle picture there, even if it was stood up, wouldn't be compliant because this discharge stack is blowing straight into your face. That's probably attached to a fume cupboard. It's exposed to the elements, and it's also fell over and it's sat on this DX unit over here. This one here is a little bit trickier to spot, but you can just see in the corner there that the bumper of the PRV has gone missing, so they've used a needle. These are all pictures that our engineers have picked up, by the way. This is actually out on site, so obviously that would be a noted recommendation at the verification. And then we continue to look at other things such as this intake on an air handling unit. We have the capillary there across the frost core, which is fine, that's not a problem. This hanging electrical thing here is a problem, and I have no idea what this is. That's a problem. And then the pigeon that have been dragged through the air handling unit, that's a problem. So again, this has been called up for verification. This is ready to be serviced and inspected, and it's obviously disgusting and not up to scratch. Those are the bits and pieces that sit in the plant room and out of sight and out of mind. These are the bits that we see every single day down in the clinical level in the operating theatre. So this is a UCV system. So how many issues can we spot? We can see the Fomex here is at the wrong angle. It's fixed in one position, so it's bound to move and pivot like it's doing over here. We have a break of the silicon seal around the stem, and the worst one of the lot is this tube that goes across here, this crucifix light on this type of system. And you'll see that the diffuser is missing and the operating main arm is here. So that spring arm could be pushed up, that could shatter, and that could go into the patient. So obviously this is also unacceptable. And then something else that only an engineer would spot. So this is the statement at the bottom here. Only the engineers can spot most things. And this is gel. Gel was removed. Gel went out as a healthy state notice a couple of years ago, but there's still some operating theatres out there with gel HEPA filters in. And this is what gel does, it changes state. So here it's quite viscous almost, and it'll hold into the channel. Because of its application and the way that it was put together, it turns to a liquid and it moves around and can start to almost turn to a liquid, and it can drop off. If you do have operating theatres with these in, and how have UCV systems have never had gel seal filters in, but we can come in and we can replace that and put PU gasket in, so no dripping would happen. So obviously that was a really quick stop tour of a lot of legislation within our industry, but we do carry out CPD sessions, which I'm sure most of you are aware of. We've delivered now to over 150 engineers. We cover Parts A and Parts B of HTML3. We go through and look at the how the UCV is manufactured. You'll see how an X-Flow 28 is manufactured in our jig in the welding shop and fabrication. We'll look at a Coanda system that's broken up, and I'll explain to you how the air moves down that type of system. And then we'll treat you as our customers and as if you were going in to witness test new equipment. So we'll go into the showroom, we'll look how you carry out the 3 tests of DOP, DPC test on filters, downflow grids, non-entrainment, and we'll show you how things work completely free to the industry, and you're more than welcome to join us. My information is there on my screen. If you scan the QR code there, you can get straight through to my LinkedIn, and then my email is on the left along with my telephone number there at the bottom. Feel free to ask me any questions now. Thank you for your time, and I will pass back over to Jonathan.
Hi, thank you very much, Mike. That was a really fascinating presentation, and obviously Howarth was among the pioneers for this sort of technology. Very interesting to hear, particularly with the additional focus that there is on infection control and ventilation since COVID. You know, the whole spotlight has fallen even more onto the subject. There are a number of good questions, which I'd like to start by putting to you, if I may. One of them is, as regards the design of the UCV, what considerations are there with air out paths particularly?
Right, yeah, so the main issue that you can have around UCVs is the layout prep room. So if you've got a layout prep room, more often than not, when you do the non-entrainment test, no matter how you design it, that would always be the worst point. And symmetry of the operating theatre is really, really important. So if you looked at the ductwork layout drawing that I've shown on the slide, it's important that ductwork remains in symmetry, really symmetrical. More often than not, if we have an issue with the airflows, people would instantly say it's the HEPA filters, it's the canopy that's concealing, but it could also be a scenario where it is the configuration of the ductwork. So we're talking about air out paths now, but before we get to that, the symmetry above the ceiling and from the HVAC system to the UCV is the first key point that you need to think about as a designer. The second key point is air out paths and symmetry past the UCV. So as I said in the presentation, air moves in an exponential manner, quicker over the surgical site and decays as it gets further out. Dead corner of the operating theatre should also always have a mechanical means of ventilation in that corner anyway. Straight down and angled is how the HTM tells you to do it. And then from a designer's point of view, you want to try and make the air out paths in those other areas, try and make them symmetrical, lines of symmetry across the operating theatre. That's what our design team do. We've just delivered an operating theatre for a project recently, and it worked absolutely perfectly. I was over there with the commissioning team when we did it. It worked perfect. 52 dB, 0.39 at 2 meters, absolutely perfect. So we can get it right at design. We'll hit our handover dates, and the patient can continue to come in, and we can start making capital in that for the trust. But we've got to really think about it at desktop stage first. So we've got to think about the symmetry of that operating theatre. Without it, you could struggle.
Thank you. And obviously, it's alongside infection control, one of the other big focuses at the moment for the whole of the NHS is sustainability. One attendee's asked, how do you feel the NHS will deal with the challenge of a mixture of red brick and campus type hospital settings? How complex an issue is that?
Yeah, a massive one. So this was one of the things that I've covered recently in my dissertation. So just 2 weeks ago, I sat in another webinar that was carried out by IES, and the way that IES are looking at it is through creating and fabricating digital twins. So they can fabricate a digital twin of your hospital of all your data, and then through that digital twin, give you the advice and guidance of where you should be focusing your money really and your attention towards net zero. So on the red brick buildings, there's a lot of inefficiencies in there. It's a really difficult task, but without modelling, I think it'd be difficult to achieve. You've got to model it first.
Thank you. Somebody else has asked, as regards building management systems and switching off the UCV out of hours, How
Yeah.
difficult is that to achieve in an older operating theatre? Because obviously there are net zero considerations here.
So I'm a key contact for Spire across the country, and this is something that we're looking at with Spire. So it's a little bit more difficult in older operating theatres. If the equipment is Haworth, if you've got Haworth UCV and an old Haworth distribution panel, then it can be done. And I'm sure with some minor changes to other manufacturers' equipment, it would be easy to do. What we need, the key part of it that we need to achieve that is the line or the cables that come from the BMS system all the way down to the distribution panel for the UCV. So if we have that in, I can replicate that. So we're never going to use an operating theatre when the HVAC goes to setback because the dilution in the space isn't good enough. But we also have other considerations to make. So that the hospital that I showed you on the screen there, they weren't considering the background temperature of the operating theatre. So it would switch the vent off, and you could not so much on that site because it's sat in the central core of the building. But some of the, like the 60-year-old hospital that I looked at, their theatres went to an adjacent outside wall. So the delta T across that wall was greater than it would be inside the core of a building. So the three things we need to do: we need to get the line of the BMS down to the distribution panel. We need to make sure that we can tie in the UCV, like we call it shutdown mode, tie the UCV shutdown mode into the AHU setback signal. And then we need a means through the BMS system to monitor the room temperature to make sure that it doesn't drop below 18 degrees. And if it does, we bring the HVAC system back on to keep the temperature at a certain level. We keep the temperature at a certain level and we can drop again. And then if it comes back on, we can drip it in through the colder winter months. Shouldn't be an issue in the summer, but in the colder winter months, that's something that we need to consider.
Thank you. Another attendee has asked if you could talk us through concisely some of the key parameters for UCV testing.
Yeah, so the testing of a UCV is laid out in chapter 12, and it's the three tests are integrity testing of the filters, the downflow grid testing, and the non-entrainment test, and they must be done in that sequence. You can't jump one in front of the other. So when Malcolm's wrote HTM, he's put DPC as an option for filtration testing because you can drop the efficiency of a HEPA filter down to E11 in a conventional operating theatre. And if you've got a filter efficiency of E11, then you can't DOP it because the DOP will bypass the filter. So in that instance, we carry out a DPC test, which we demonstrate on CPD day. Once that test has been done, the filter frame has been sealed and everything from an integrity point of view is there or thereabouts. You would then carry out a secondary balance of the ventilation system. So as a commissioning engineer, you would approach the site and it would already be proportionally balanced and everything would be set up. The filters go in. The filters don't add any resistance to the system, but the impact can come from the UCV recirculation fans. The recirculation fans can draw on the system. So if you draw on the system, it can affect the volumes that are in the other rooms. So if that happens, when we validate, we look at design plus 10% in every room. That's an HTM, City Commissioning Codes of Practice. That's a key thing that we've got to look at. So filters go in, we do a secondary balance to make sure that we're at the design volumes that the designers put out for the commissioning team to achieve. Once that's happened and we prove pressure cascades are correct, we then carry out the 1 and 2 meter readings on the UCV terminal there. Once that's been done, we move on to the non-entrainment test, where we take an unHEPA'd supply air from the prep room, the anaesthetic room, sample that with a particle counter, and we count round in 13 positions on the UCV. It's worth noting as well, before we go down that route of doing all the final balancing and everything, I recently spoke to Malcolm about permeability testing of the operating theatre. So when it's at building stage, we open all the doors, we zip a permeability door on, blow up to 50 pascals, measure the decay, measure back to 50 pascals, so positive 50, negative 50, measure the decay again. And then when we get to them areas where we're testing the UCV, we're so tight on program, we know that the envelope of the room is at an acceptable level, so you can confirm that your pressure regimes, everything's been sized right, should be bang on. So everything must be done in a chronological order. You can't skip one in front of the other.
Thank you, Mike. The questions are quite varied, so excuse me if they sort of go from one subject to another. Harm Hollander has asked, one of the attendees, what are your top 3 recommendations to architects in this area?
Symmetry of vent. So they need to give the architect needs to give the M&E designers the right areas to get the vent in. Symmetry of vent, access to the VCDs and everything. So where I've spoken about these, the canopy dropping sometimes they're dropping 2 and they might take the anaesthetic in the prep room off. It's not the end of the world. It just makes things a lot more difficult, and you can add noise to the system if you do that. So obviously we need to, from the architect's point of view, space in the ceiling and space to get the duct in, which can be a bit of a constraint sometimes. And then considering the air out paths, sometimes the architects do things because it might look better, but the HTM is very clear in the way that things should go. So slanted low level out paths, adequately sized air out paths. So that, like thinking back in projects that I've had in like yesterday, undersized air out paths can cause issues with entrainment. Enough space around the UCV. So from the outer edge of the UCV, give us at least 1 metre to a wall, and we need to work within the parameters and the guidance around that. So I would say that ventilation space for the mechanical system in the plant room and the drop in the ceiling voids, air out paths and adequately sized air out paths, and space in the operating theatre. We don't want to try and shoehorn things in.
There's a lot to consider then.
Yeah, there is. It's not just. So sometimes when things go wrong with UCVs, people say it's the UCV because that's the bit that they can see. It's the UCV in the ceiling that's failing, so it must be the UCV. But they're so finely balanced on a tooth comb, it doesn't matter the manufacturer, it can be any manufacturer. They're so finely balanced on a tooth comb, it's important to engage the specialist as early as you can in the process. And at Howard, the design manager over there, Barbara, and our sales director, Tom, they work very closely with consulting engineers as they're going through the process, and we'll work together as a team to make sure that it's right at the end, because we know the pain if it isn't right at the end.
Understood. A specific question here from Simon Burke, who says, is the ductwork pressure test only required on new installations or when plant is maintained or life cycled after 10 years?
So I would say, so new equipment certainly. Life cycle would be difficult. Sorry, life cycle, it should also happen as well. It depends on the level of life cycle, I suppose. If you put in a new UCV, a new air handling unit, and a section of new ducts, then I would recommend that you fully pressure test the full system. If it isn't, like I said about the derogations before, that needs to be discussed right at the start, and there needs to be an acceptable reason why it's not going to happen. And the validator needs to be made aware of that early on. And if he isn't, he's well within his rights not to accept that system until it's pressure tested and proved that it's adequate. One of the authorising engineers that I deal with, when I have a problem, I have a couple of trusted ones that I go to. And one of the things that he says is, we wouldn't accept losses in a medical gas system, so why should we accept it in a ventilation system, which made me think slightly different about it. And he's obviously right. Sometimes we go into you can go down air handling units on site, you can feel the loss in the doors, and you can feel it around inspection hatches on positive ducts. So imagine what it's like on extract ducts or bits we can't see in the ceiling. Or there is other companies out there. So Leighton Hospital, I'm sure you won't mind me speaking about there. They've recently gone through an aeroseal process where you can't get to existing ducts, and it's like a foam that sprays through. Now that's the first time I've really properly seen that used in healthcare, but it's gone through as a case study. We're verifying that soon to confirm the results that aeroseal have got. But that's a solution to people within the industry. If you've got unaccessible bits of duct, it might take you weeks to take ceilings out and drop a duct out of a riser, and these are time-consuming jobs to do in spaces that are never shut. So there's options out there. If anybody's got any questions about it, give me a shout, because I've got the reports for aeroseals. I'd be happy to share them.
Thank you. The next one's almost a statement, but I guess you know the answer to this. Stephen Royce has asked, he said, theatres often prevent annual validation from taking place. Is that something you find in the NHS with the pressure on time for surgery, etc.?
Yeah, so it isn't uncommon for our engineers to be going to operating theatres at 10 o'clock at night now. We go in late at night, we're going at weekends, we're going in Sundays. Operating theatres have become spaces now that are very rarely shut. There's only a handful of trusts that I know of that still have their audit days that we have on the contracts at Haworth. Yeah, and I think we're obviously trying to scramble back a massive waiting list within the NHS following the pandemic. And yeah, I agree with that. It's very difficult to get into these spaces. Very difficult, not much more difficult than it was 5 years ago anyway.
Thanks. I hope your voice is holding up all right, because I know you've had a sore throat from the last couple of days. A very interesting presentation. It's generated a lot of questions. The next one is, with the new HTM, are there any obvious energy saving opportunities? You mentioned a lower air change rate.
Yeah.
I think you've covered some of this, but if you can address that.
Yeah, so I'll give you a bit of background around that. So when I speak to Malcolm about the air change rate, the energy saving, in the old document in 2007, we were allowed to use belt and pulley arrangements in our fans, and we aimed for 25 air changes because of that. So when the new HTM was written and we moved to EC plug fans, and the belt fans have been completely abolished now, he reduced that air change rate, because the idea was that if we had a belt and pulley fan arrangement in the air handling unit, we would set it up at 25, and as the belt would slacken and start to decay, it may go down and the air change rate would drop down sort of 22, 21, 20, but it would never cause a microbiological issue in the operating theatre, because we had someone like us who'd go in, your belts need changing, we change them, and then it'd be back to 25 air changes and no problem. Now, there's no efficiency losses in a plug fan or an EC fan, because it fully runs on tilt for forever. And there's different methods we can use as well in the air handling unit. We could use a fan wall, for example, where 4 or 6 EC fans will sit across the plenum of the air handling unit and all run at the same time. And then if one drops off, the others can give 80% of the flow down the air handling unit. So there's been changes in the HTM to support the net zero. When we wrote it, I was part of the group that collated it. We went down to London, there was a chap there, and he was constantly bashing on about net zero and making sure that things were more efficient. The ventilation strategies inside HTM now give different options to the designer on how they're going to control and move the vent. As part of my dissertation at uni, I've looked at new technologies around the stuff that we do, new fans that we're using. They drop down by about 0.6 of a kilowatt. So as manufacturers, we're moving forward as well and becoming more energy conscious about what we're doing, and the embedded carbon and things. We're discussing that a lot more as an internal group now, which obviously ties into the NHS full supply chain. Because I think if we look at the NHS as a full organisation and the guidance that they've got around net zero and trying to achieve this really difficult thing that they've got to do for Scope 1 in 2040, I put a questionnaire out and 115 people answered it, and one of the things said that the NHS will be privatised before it goes net zero, and that stuck in my head for the second part of the full second part of the thing, and I become more and more pessimistic the further I got through the document. And the start of the title was how they were going to achieve it. It's going to be super difficult to do, and the guidance that I put in my dissertation, I've concluded with this will chop it down to a certain extent, but we need to look at it holistically across the NHS to actually get to net zero. It's going to be very difficult. And as I put another thing in there about considering the air change rate to the patient, we go and do a rebalance on a system. We'll knock it up to get it to the right air change rate. It's not uncommon for us to go back, and that's been pushed back down again. It fails next year. So there's an education piece as well that's missing within the NHS as well, I think.
Thank you. Next one's quite a sort of practical issue. Hassan Ahmed has asked, I understand the new HTM asked for 1 metre of clear space around all sides of the OT. However, in refurbs, this isn't always possible. What are the implications, he asks, of not achieving 1 metre?
You would more than likely have an entrainment issue. So the third test that we carry out, we do filter integrity, downflow grids, and entrainment. That could cause you an entrainment issue. You could get air coming back into the clean zone. So when we lay up on that differential colour on the floor, you could have something rolling back into the canopy. What I would suggest, if you ever come up against that sort of challenge that you've got on a project, I would suggest that you approach the manufacturer, and then the manufacturer can take a look and say, have you tried this? Have you done that? Could we move this over here? What about if we included extra low-level outpaths at this point, and we can sort of systematically take the issue apart together as opposed to you doing it on your own. That's something that the team at Haworth do. We do that pretty frequently. We try and give the best solutions to the customer, whilst at the same time giving them products that we know will work when it comes out of the box.
Thank you. Another very topical question. Gaston Shabba, who I think is a professor of building services engineering who regularly contributes to HEJ and is very expert in his field, has said, he's asked, to what extent can the filtration system deal with P2.5 particle and ultrafine particles found in the air? And he's got a second question. What mechanism is involved in capturing COVID particles, given the size of the particles?
I don't know if that's a bit
So I
above
don't
my
know
pay.
whether that's an easy
So
question to answer.
one thing to note about the COVID thing, there was a lot of confusion in COVID, and there was a lot of inquiries into Howarth about making operating theatres negative and all this carry on. So again, I'm not a microbiologist, I'm an engineer ultimately. And when it comes to actual capturing sizes of particles in filtration and what have you, I'll probably have to speak to someone at Camphil or AAA or somewhere like that. But we know that dilution is a key to control COVID. And when I've worked with the clinical team down at the hospital down in the southwest to do the power consumption and turning it on and off out of hours, they actually found that the cleanest space of the whole hospital, including the pharmacies and CSSDs and everywhere on site, was the operating theatre. Now they have X-Flow 32s on this particular site. They've done lots and lots of testing for background and assessing air change rate and aerosol generating procedures and fallow time between cases. And they found that within 2 minutes, an operating theatre is purged and it's good enough to go back in with whatever has been going on in there. And the clinician that's doing that is part of his PhD, and he's going to be publishing that within the next year or two, I guess. I don't know when he's going to finish. So not my area of expertise, but I can capture the list of questions at the end, and I'm more than happy to do some digging around the industry, and I'll drop that chap an email, not a problem.
Okay, I'm sure Gaston would appreciate that. Another audience member or attendee, Sean Higgins, has asked, what are the new standards for minimum HEPA filter standards, and how does this affect validation and most penetrating particle size? Have the requirements for the standards of filtration in effect reduced?
Yes. So in the last HTM, we could drop down still. So I think off the top of my head, I think it's down to E10, which is a 95% efficient filter. At Howarth, we fit H14, and the reason we fit it is for the terminal of the unit and to build pressure up within that system to get the exponential airflow. Now, as part of R&D, we're building an R&D team over the next sort of 6 months, and we're going to be looking at different factors around this, and one of them will be filtration, because other manufacturers in the industry fit a lower grade of HEPA filter, which is fine for the environment, that's fine, not a problem. And the only way to integrity test those is through DPC, discrete particle counter. When we go up to H14, we use the DOP method where we would blow smoke in and we measure with a photometer. So yeah, it's fine. You can go down to I think off the top of my head, I think it's H10 or H11, 95% efficient filter. It's in HTM. If you have a quick search of the document, you'll see a table in there. It gives you all the facts and figures in there about filtration.
Thank you, Mike. Phil Eagles, who I would assume from his question is probably in the Estates and Facilities Department at Milton Keynes Trust, has asked, he said, here at Milton Keynes, we're working on a Salix project that includes photovoltaics, new roofing, new ventilation plant for theatres, and windows being upgraded to double glazing in general areas and theatres. So this is all very relevant. I think that's more a comment rather than a question. So
well, that's exactly the right thing that you should be doing. When we spoke earlier about IES modelling, the IES model would have pointed the trust in that direction, but it already seems like they're moving in the right direction. So that's great news.
Thanks. Gaston Shabba, professor, has asked another question, which hopefully is not a too challenging one. I don't know, not being my particular area of expertise. He said, what measure will be put in place to clean ducting systems given the higher likelihood of dust accumulations and hotspots due to organic matter deposited inside the ducting system? And he's supplemented that. Is there any sensor-based system of monitoring dust thickness in ducting? Again, I don't know whether that's those are both questions that you can answer.
Yeah. So duct cleaning, obviously, if we take a look at a system from day one, that should obviously be cleaned and swept from day one, and then it's up to the trust then to keep on top of that annually. As part of the verification that we carry out, we inspect the ducts. We'll open a couple of hatches, check there's nothing laying in the duct, and then cover that up. And if there is, and we clean it, it's covered by a visa document, TR19, where companies can go in and do surface swab testing. Now, a couple of years ago, the same year that I looked at the DAX unit, I had a demonstration with the Aeroseal guys, and I'm sure it was the same stand. They had some artificial intelligence that sat inside air handling units, and it could monitor things like coils and filters, and it would indicate when things were getting dirty, and it could predict when things would need to be changed. Now, I don't know if that could go down ducts, obviously it's pitch black. I don't know if that could go down ducts, but if you're getting things annually checked and verified, like you should be, in line with HTML3 Part B, then that should be picked up anyway. And then we'd go back to someone like duct busters, and then you get the TR19 sweep done of the ducts. And it's picked up as well in conventional spaces where we do microbiological testing. The first point that we would look at, theatre at rest, no greater than 10 colony forming units on a plate. We do an SDA and a TSA plate. Sit that down. The first port of call we look at is clean the theatre. If it fails again, then we look at bypassing the air handling unit and ductwork cleanliness. So there is tests in place to get it, and there's a document all about it at TR19.
Thank you. Somebody else, Carl Sykes has asked, are compact ventilation units with electronically commutated fans, single units without backup fans, acceptable?
I'm guessing we're talking about in the air handling unit there. So it's acceptable to have a single fan inside the air handling unit if a replacement fan is wired and local to the air handling unit and can be replaced in something like 30 minutes, or it's something along the lines it's worded in HTM. So as long as you've got a robust method of replacing that fan, the HTM says that that's acceptable. I'm not sure of the actual section off the top of my head.
Thanks, Mike. It's quite a specific question from Gavin Goulden, who asks, what is the frequency of maintenance for a UCV?
So
and I guess he's talking about HTM specifications here.
Yeah, so HTM says annually check, so every 12 months. Now, as the manufacturer, we say every 6 months the UCV should be checked or serviced. And the reason we say that is because around the outside of the canopy on the perimeter of the UCV, there is a pre-filter. Pre-filter is a G4 grade standard type panel filter. And what happens is, as the lint and the bone dust gets thrown about the operating theatre, that gets drawn back up in the eddy currents of the air going back up to the canopy. And after 6 months, they'll be thick with lint. They need dropping, the door needs cleaning, filtration needs replacing. And then once that happens, we'll just do a quick check of the 1 and 2 meter readings on the canopy. Some clients still get us to do that, but some clients say, no, it's okay, we'll replace the pre-filters ourselves, we'll buy the pre-filters off you, we'll do that ourselves, and we'll just annually check the airflow tests. So it's up to the customer. As long as it's done annually, that's fine from a compliance point of view, from a manufacturer's point of view, twice a year.
Thank you. This is another net zero and energy and carbon saving related question. Paul Prendergast has asked, roughly how much energy would be saved if the UCV was switched off each night by the building management system?
So in the conclusion for my dissertation, it'd be interesting if I could bring my equipment to Paul's site and I'll clip it on and see what's going on. But for my dissertation, it was 60% from a straight kilowatt power out, yeah, 60%.
Catherine Zeliotis, who I think from knowledge is an architect, has asked, do the increased requirements have an impact on the size of the operating room?
The increased requirements in relation to what, sorry, Jonathan?
She's not said there. She said just do the increased requirements have an impact on the, I mean, she may be talking about airflows. I'm not sure. It may be one you need to come back to her on direct on that.
There's a standard room size in the HBN that says operating theatres are 55 metres squared. You put that volume in, you should get about the right air change rate at a similar size ceiling at 2.8 3 metre ceiling. So yeah, there's standard layouts. But my information is on the slide. If she wants to elaborate on the question, feel free to contact me.
Sure, she can obviously get in touch with you. Nigel Baker has asked, how independent can you be when validating your own canopy?
It's a difficult one. So the way that so one particular site that we've got, they have a clause in there that their approved supplier has to carry all the validations out. So the way that we split it and differentiate between the two at Haworth is we have the capitals team and the service and after sales team. Obviously, I look after the service and after sales team. So I draw a line right down the middle of the sand and say that side of the system is delivered by the capitals team, and we're going to work on behalf of the estates and facilities team, not the capitals team. I'm going to make sure that it's fit for purpose and it's put together correctly, and we'll assess the commissioning document and everything that you'd expect a validator to do. Notwithstanding that, it is very difficult to go down that route. When I go out and validate now, for example, I was out last week validating endoscopy suites, a refurbished endoscopy suite. We'll go in and do intensive care, HDUs, recoveries, ICUs. They're the type of areas we normally go. We have gone out and validated third-party equipment as well, which again could get a bit muddy if things go wrong, and it did significantly go wrong. But I think if you operate in a manner with integrity and showing that you're trying to do a good job, I think the authorised person can see that. And the only thing that I'm interested in is that the NHS gets what we pay for. And the trouble with validation is if you don't capture it at that stage, it's going to be like that for the next 30 years. So the validator has to be really robust, mechanical and electrical, to appreciate the BMS system and everything else that's required of HTM, all the HPNs. But that's the way that I differentiate it in my team.
Thank you. Another quite specific technical question. Mike King has asked, can you fit EPA filters in older canopies, or have they been designed for H14?
No, we could reduce the grade of the HEPA filter, because the HEPA filter is a standard size that's made for us by filter manufacturers. So we could look at changing the pleats in that, but we'd have to run it through an R&D process first. We don't know what reducing if you reduce the pack, it reduces the pressure. We don't know what that does to the system and the exponential airflow, so we'd have to check that first. That's the only issue you'd have.
Thank you. Another question here. Danny Madden from SI Sealy has asked, who is the responsible person for ensuring that there's a ventilation safety group within a hospital?
I think that rests, or it should rest with the estates management, I think. I think that'd be the most sensible place to start, because the estates management team would be looking after water, electric, lifts, all the other disciplines that are on site. I think it would be them that would initiate that. And then maybe that would be managed by the AP for vent. Speaking about the authorising engineer and the validator, it's also important to note that they should be employed by the customer. So that's a requirement of HTM, is that they work for the customer, not necessarily the builder. So that's another dynamic way of looking at it. The job that I did last week, our order came through from a builder, and that was the way that the NHS wanted to do it. But I believe that that's the way it should look. The estates management should look after the ventilation safety group and tie all of those parties together, I think.
Thank you. Tom Ford has asked, how closely do you work with fire engineers in the initial design of critical ventilation systems?
So if I think back of all the other projects that we've been involved with, and we look at HTM says something about keeping AHUs in fire compartments and other bits and pieces. We look at the positioning of fire dampers and making the actual operating theatre a fire envelope. The dirty utility, more often than not, is its own area, and then we look at keeping the operating theatre its own fire envelope. Now, that's normally discussed as a group and not necessarily just with the fire officer, and if there is any fire officer sort of concerns, then they're brought into the discussion at a stage of the process that's when it's going through tender, I guess, and design, probably sort of the early stages of the process. Again, it sort of relates back to the permeability test that I spoke about earlier. So when Malcolm's looking at the permeability test now, he's saying that all doors of the suite should be open, and we pressurise this suite from the scrub and monitor decay from the scrub with all the doors to the anaesthetic room, the prep room. We look at that as one envelope, and that was what Malcolm was saying to me just 2 weeks ago. But in terms of actually dealing with fire officers, personally, I've never really dealt with them that much, but they would be involved in the process at some stage.
Thank you. Danielle Taylor's asked a question. Doesn't the HTM, and this is 0301, presumably in rewritten form, require that the validation is undertaken by an independent personal company?
It does, yeah.
Yeah.
It does. Yeah. So the validator should be independent from the whole process, employed by the customer. But when you have this situation where we get called in to do the validation at the same time, I think it's more of an area where the customer is trusting that validator to do a good job. like I said before, the validator should be mechanical and electrically able. HTM00 should be competent, should be very familiar with the systems that they're trying to set up, and finding those people within the industry that are strong enough to hold people account is difficult. So when we get these inquiries coming through, and when I get to start a validation, my focus is this going to be right? We're under a lot of pressure when we get to validation. This needs to be open. There's patients coming in on this day. The program's slipped, and there's builders in there hanging doors. We're under tons and tons of pressure, and it takes a strong person to actually stop it. And if you've got a good ventilation safety group around you, a good authorising engineer, some authorising engineers are really good at this. They will be on your side. You feel sometimes like you're a bit of a stickler, but they'll be on your side and they'll stop it with you. But yes, the validator should be independent, and it should be employed by the trust.
Just a couple of other closing questions. Hassan Ahmed, who asked an earlier question, has said, last time I checked, I don't think there is a standard 55 square metre theatre big enough for a 3.2 by 3.2 canopy when including the 1 metre clearance on all four sides. He said an important question to be asked at the project inception, I guess.
Yeah, so when we talk about air change rates and PFI hospitals and all the other bits and pieces, one of the reasons Malcolm changed to actual air change rates as opposed to flows that were noted in 2025, because we were getting these massive operating theatres. Now, the question of the 55 metres squared operating theatre and fitting a canopy in, the best person I could speak to about that would be Tom, because he knows the numbers of measurements off the top of his head. So again, I can follow that up. But you are right, it would probably pretty close, but we need to keep that meter. It's a regulation. We've got to abide by that.
And a final question, James Bowman has asked, you mentioned less than, is it 10 CFU during micro testing? Is this in the new HTM, he's asked? Yeah,
so it notes it in HTM. So we look at a theatre at rest is no greater than 10 colony forming units on the plate, the STA and the TSA plate. A theatre in use though would indicate that the ventilation system is functioning to an adequate level. So obviously with the theatre in use, there's movement and there's people in there, so then we would look at 180 CFU. I've worked at Howard for a long time now. I've never, ever been involved with monitoring a live operating theatre, but when I spoke to an authorising engineer about this last week, he said that gives a better indication of the actual ventilation system being effective and working, because we talk about getting a good mix of air. The throw from the diffuser needs to be satisfactory. We need to retrieve 0.2 in a conventional operating theatre, but it doesn't actually state where those measurements should be taken. So there's lots of things that need to be considered around the 10 CFU. So 10 CFU is at rest, 180 CFU is in use. That's the long and short of it. I touched on it a little bit on the CPD day. You're more than welcome to come. Have a listen.
Thank you. That's great. One question from me. I mean, how much has the concern over the greenhouse gas emissions, the effect of some of the anaesthetic gases had on your thinking at Howarth?
Yeah, so the desiflurane, sevoflurane, there's a couple of anaesthetic gases that are being emitted now, isn't there? And they're doing loads of work on this at MFT, so with the Shore Manchester Royal Infirmary.
And the Newcastle, I think.
Yeah, so it's a massive topic at the moment. From Howard's point of view, not a massive amount, to be honest with you, Jonathan, because it's not really our area of expertise. When we're supplying a medical gas pendant, we supply what is spec'd by the people who know what they're doing. But I know that the team that I work with down in the southwest, they're a team of there's predominantly anaesthetists. So this is why I know about the bits and pieces, because they taught me about it. So from Howard's point of view, not a massive consideration, but from the NHS's point of view, something that they're phasing out, I believe, which is obviously a good thing.
Thank you very much. A number of people have asked whether the slides will be available subsequently.
I can distribute the slides by HEJ, if that's all right, Jonathan, yeah?
Yeah, that's absolutely fine. Yeah. Well, that concludes the questions we've got, and it concludes today's webinar. Thank you very much, Mike, for a great presentation and for your stamina in answering a huge range of questions and being put on the spot on all sorts of issues. I think the number of attendees and the number of questions we've had just shows how important the whole area of ventilation is in healthcare at the moment.
Yeah.
Delighted you were able to take part, and thank you very much to all our attendees for attending. Thanks again. Thank you, Mike, and goodbye.
No problem. Thanks, Jonathan.
Cheers.
Bye now.
Bye.